Okay, in our previous video, we looked at the concepts of equilibrium and thermodynamics and basic chemical reactions as a review. Now we are going to be examining free energy and thermodynamics in biochemistry. This is a little more complex now, because what we have to consider is the thermodynamics of potentially coupled and sequential reactions. What I mean by that is that a simple chemical system where we take a reactant and make a product, and these reactions, of course, are mostly reversible. We have A reactant forming B product, and this, of course, will have a simple equilibrium constant of the concentration of B over the concentration of A. This can achieve a steady state situation, so we can measure A and B and determine the equilibrium constant. Biochemistry is a bit more complex because oftentimes we will have similar chemical reactions, say reaction 1 that will lead product reaction A to form product B, but then in biochemistry we have pathways so that reactions can form in sequence, so that the product of one reaction can now be the reactant of a subsequent reaction. For example, reactant A can form product B in reaction 1, and then product B can be the reactant for reaction 2 to form product C, etc. This has a profound effect on the concentrations of each one of these reactants and products, and these are all interlinked by these subsequent related interconnected reactions. So as you can imagine from this scenario, achieving equilibrium is virtually impossible in biochemistry because we are coupling these reactions in sequence. So now, how we calculate free energy in biochemistry is that we have to add an additional factor from what we've seen before. So what we're calculating now in biochemistry is free energy change to determine if a reaction is going forward or backwards, just as we saw in the simple thermodynamics of a simple chemical system. But now in order to do that, we need to calculate that free energy change by incorporating the standard free energy change, delta G 0 prime. Remember, this is the free energy change that is inherent property of the particular reaction. And now we are going to modify this value by including a value that multiplies our gas constant and temperature with the natural log of the product over the reactant. Very similar to what we've seen here calculating standard free energy change, but now this is the observable concentrations in the moment. What does that mean, in the moment? That means that at any particular time in a biochemical sequence of reactions, if we want to determine the specific free energy change of a particular reaction in a sequence, we can measure these concentrations at that moment, put that into this equation, and determine if this delta G is going to be negative and move forward, or positive and move backwards. Now, how do we do that? Let's say that we have a very high concentration of our product, B. let's say we also have a very low concentration of our reactant A in this first step of this reaction. This will give us a very large number. Let's say much greater than 1. This particular value is called the mass action quotient, and it's abbreviated Q. This is not the equilibrium constant. This is a mass action quotient. Concentration is determined again in the particular moment that we are observing this reaction. Now, if we have a large value here that is much greater than 1, if we place this into calculate the natural log of the number that is much greater than 1, this is going to end up being a natural log, going to be a positive value. So then the natural log of the mass action quotient of Q, if this is a large positive number, multiplied by RT, add the standard free energy change, this is going to give us a positive delta G. So under these conditions, with a high concentration of product and a small concentration of reactant, by doing this calculation at this particular moment, the reaction is going to be predicted to go backwards. And that's because the forward reaction, based on our calculation and our concentrations of our reactants and products at this time, gives us a positive delta G. That means the reverse reaction will give us a negative delta G, telling us that the reaction is probably going to be moving from B to A. Now let's look at this reaction a little differently. Let's say that we have a very low concentration of product B and a very high concentration of reactant A. This you could envision at the very beginning of a reaction. So if we have our sequence of reactions in a biochemical pathway, if we put in a lot of reactant A, we are very much likely to be starting this reaction forward. So this is going to give us a very small number, which is going to be very much less than 1. And again, if we take this value, being our mass action quotient, less than 1, this is going to be a negative number. Natural log of less than 1 is a negative. That is going to be multiplied by two very large numbers. So this is going to be a very large negative factor in this equation. That will more than likely offset the free energy change inherent of the reaction, and it's going to give us a negative delta G. That will tell us that if we have a large input of reactant A, the reaction sequence is likely to go from A to B because we have a negative delta G. And therefore, the reverse reaction from B to A is going to have a positive delta G because we have very little B that could form A. Now, another important consideration in biochemistry is that standard free energy changes are additive. So let me partition off this corner of the paper. Standard free energy changes are additive. Now, why is this important? Because in biochemistry, when we have pathways, in order to keep a pathway going, we often need to couple chemical reactions to push a reaction in one direction, which essentially means forcing a negative delta G. So let's look at a specific example. A particular biochemical reaction, we are going to take glucose, 6-carbon molecule that is going to be used for energy production, and we are going to add inorganic phosphate to that. This is a reversible reaction. We are going to form glucose 6-phosphate as our product plus water in this reaction. And if we look at the delta G 0 prime of this reaction, this is a positive 13.8 kilojoules per mole. In other words, this is an endergonic reaction. This is the first step of oxidizing glucose so we can generate energy. This is the entrance into the glycolytic pathway. So this is an absolutely essential reaction that has to occur and does occur. But we have a positive delta G, standard free energy. So how will this reaction ever work? Well, let's consider another reaction where we're going to take ATP. We're going to perform a hydrolytic reaction, hydrolysis, meaning we're going to add water that is going to modify a bond on ATP. And we are going to produce ADP plus inorganic phosphate. Now, the standard free energy of this reaction is negative 30.5 kilojoules per mole. This is an exergonic reaction. This is very favorable. Look at that big negative delta G. Now, if we couple these reactions, this is where the standard free energy changes are additive, and this will help our reaction move forward. So let's add these two reactions together. And what we are going to get is glucose plus ATP will form glucose 6-phosphate plus ADP. So what we simply did is added both sides of the reactions sequences, and this is called a coupled reaction. And this happens very often in biochemistry. So what do we do with this reaction? We can calculate the delta G0 of this reaction by taking our positive 13.8 kilojoules per mole, and because it's additive, we are going to add now our negative 30.5 kilojoules per mole. We add these two values together, and now we get a negative 16.7 kilojoules per mole. Will this reaction move forward? Of course. So we've taken an unfavorable reaction with a positive delta G, and we've coupled it with a very favorable negative delta G reaction, added these together, and now the entire reaction sequence is ensured to move forward because we have a large negative delta G. Again, this is the additive nature of standard free energies coupling reactions.